Yesterday, we built a foundation up in being able to use big data sets, which I said we'll see today really enable more complex machine learning. And in particular, we learned how to use Spark, which is a framework that we're going to be able to build on again with our machine learning itself. We're going to use more of the Spark ML lib to do a fairly complex and representative of real world application this morning, the recommender system. This afternoon, we'll take a very different turn and we'll use a different framework, TensorFlow, to build a very different type of algorithm, deep learning or neural nets, to do a couple of other very different applications. So we're covering a lot of ground here, but I hope we're building up some momentum from yesterday. So the recommender system that we're going to use this morning as an application, I like it because it's very intuitive to understand what we're trying to do. Everybody's exposed to recommender systems these days. Every time you go onto Amazon to buy something, it's recommending products that you might like. As a matter of fact, all those insidious, awful ads that the net bombards you with are all recommended to you for one reason or another. They're not just randomly selected ads. But more helpful recommender systems like Amazon One or like Netflix, for example, are trying to genuinely help you choose the best products, expose you to things that you might think you'll like the best. Netflix in particular, right, says here's a movie that we really think you might like and can even used to be able to project star ratings. Netflix seems to be getting away from that, but at the time when they launched this competition, their goal was to very much improve their star rating projection system, and it was important to them to the extent that they put $1 million prize on this competition. We're going to do the very same application and use the same data set that was used in that competition. So this is exactly what they did. We're going to use a smaller data set at first to start with, because that way we can process it and learn things, train the algorithm in a matter of 30 or 40 seconds. But we do have the full large data set there for you to use, which takes longer to train. And when we're done, we'll give that a shot as well. So this is, again, intuitive and easy to understand, but it's also going to introduce some more general machine learning principles. So we're going to find ourselves having to employ some things here that we talked about yesterday. We talked about some general machine learning principles, and we're going to find ourselves rolling in some new ones that we'll use later on this afternoon with neural nets and deep learning, and you'll use indeed throughout your career with doing any kind of machine learning. So it's a very good application from a number of perspectives. So once again, what we want to do is we want to be able to recommend movies to our customers. So the Netflix data set that was used in this competition is also pretty easy to understand, intuitively simple to grasp. You can look at the text files. We're going to have 2 text files that are going to get read in and utilized by this algorithm. One of which is just a simple file that gives every movie, assigns every movie a number. We're going to use numbers for our movies throughout our rating system here. The system's obviously, Spark is it's easiest and simplest to manipulate numbers instead of strings. But when we're done, we really do want this to report user or names to the user. We don't want it to just say you'll like movie 32. We'd like instead to say you might like movie 12 Monkeys with 3 stars, we project, or you'll hate it with 3 stars. So we're going to have a very simple data set that'll just tie all of our movies to a particular number. Now, our ratings data set is really where the action is at. That's where all the interesting information is. And that gives, for every movie number and every user, a particular rating. Well, what it actually gives us, it doesn't give us for all the movies. What it gives us is for the movies that users have seen, it will give us their assigned rating. So in other words, a user 2 in this case, the users all have numbers that are anonymized in this user database here and in the competition. So user 2 has seen, in this case here, 4 movies. If we look in our entries in the ratings data set, movie 144, 150, 153, and 161. And we could go back into the data set and see exactly what those names are. And when we're done, again, we'll assign names to the movies and we'll be nice and friendly for the users. But when we're looking at the data, we'll just stick with the movie numbers. So when we're developing our algorithm. So user number 2 has seen movie 144. They gave it 3 stars for its rating. And here's a timestamp of when they viewed it. We'll find the timestamp's not particularly useful to us, so we won't be using that as we go along. But we will find that the user movie combinations with their ratings is essential. It's going to allow us to project new movie ratings for all the users. And again, it's a text file sitting there in your disk on your drive right now. You can look at it, and it's human readable, you can edit it and whatnot. We won't do that. We're just going to suck it into Spark and work on it like that, but it is a human readable file. So essentially what we're given, if we start to kind of organize this data here, is we're given a very sparse number of ratings for all the potential movie user combinations. In other words, if we have, which we have in the Netflix case, 480,000 users, and we have 17,000 plus movies, and we plotted out all the data points we're given, this is what it would look like for all the users versus all the movies. And this makes sense, right? Users have only seen a small percentage of movies. You as a person have not seen a majority of movies available on Netflix. And so it's a very sparse entry table here, and we're going to treat it as a matrix. And it's, I guess, a little better than 1% filled out of the 8 billion elements that are available to us. So this is our starting point. Now, what we'd like to be able to do, though, is to project for any given user what they would think of a movie they haven't seen. So we'd like to fill in this matrix so that for any given user, we can go down here and say, oh, this movie here, we think you'd give it a 2-star rating. You wouldn't like that very much, but this one you'd like. So this is what we're doing. We're starting with this, and we want to end up with this. So again, it's, I hope, intuitive and easy to understand for everybody what we're trying to do with the data. But if you think that that's a difficult task, think about as a human being how you might approach this problem. So if you're, a video store clerk, back in the days when there were still video stores, and you might observe that a user coming in really liked Annie Hall and the Purple Rose of Cairo. And as the knowledgeable video store clerk, you might recognize those are both Woody Allen movies. And so you might say, you know what, maybe this user might like Zelig. That's another Woody Allen movie. And so you're kind of making recommendations to them based upon a latent variable, hidden thing that doesn't come directly into the calculation here. So it's not that hard to believe that we can start to find commonalities between users and what they like, and begin to recommend things to them. And again, it might be a director, it might be actors, it might be genres. There's lots of latent effects that we might come up with that allow us to start to predict what users would like. That's what our system is going to do. Now, we have a very large matrix, 8 billion elements, as we said, in this particular case here. And we can imagine today it would be even much larger. This is only 17,000 movies. We can imagine there are a lot more movies and maybe a lot more users these days as well. And so that becomes a difficult matrix to manage. And so we're not going to try to manage the whole matrix. Instead, we're going to try to compress the matrix down into a couple of smaller matrices. Now, as I said yesterday, linear algebra is kind of the standard language of machine learning, and you should get comfortable with it. But if you're not at the moment, if your linear algebra is a little rusty, the only thing we're really going to need to understand for this application here is how to do matrix multiplies. And that's because what we're trying to do here is generate elements for a large matrix by taking 2 smaller matrices to generate each of those elements by matrix multiplication. In other words, if you remember basically how matrix multiply works, you take this column and multiply it by this row, and we can get this element that corresponds to that column and row. So that's the simple mechanics of matrix multiply. That allows us to try to represent a large matrix by having smaller matrices here, because as long as this matrix is tall enough and as long as this matrix is wide enough, we can represent any given point that we need here. Now, obviously, we have fewer points here than we have over here. That should right away tell you, if you don't know anything about matrix decomposition, right away that should tell you that we're going to have as we multiply this row by this column here, we're going to have fewer and fewer elements to give us the right row and column to give us that full data, and we're not going to be able to represent faithfully the original elements here in this matrix, right? Because we have fewer elements. Common sense tells us we could reduce this K all the way down to 1. So we've got 1 column here, and we've got 1 row, and that's going to give us 1 element to multiply for each one of these things here. Obviously, we can't reproduce all the data that was in this original matrix. So we're going essentially with a lossy compression scheme here. So I hope everybody's at least comfortable with, again, that matrix multiply scheme, that you multiply to give a row and a column here, you multiply the appropriate row and a column from these 2 matrices, and that means we can make these matrices much smaller here, but we're not going to be able to recapture the original matrix here. This original matrix is 8 billion elements, and we can get this thing all the way down to 17,000 by, what did we say, however many users there were, 80,000. So we can get this down to 17,000 by, how many users were there, just so we can keep some real numbers here. 480,000. So we can obviously have a lot fewer elements to generate this original matrix here. So we're going to lose data. We're going to have a lossy compression scheme here. So again, we're coming back to something from yesterday here, which is that a lossy compression of our data might give us a more tractable problem and might give us better insight. Well, it's definitely going to give us a more tractable problem here because we no longer have to juggle this 8 billion element matrix. We don't have to keep that in memory. Now the question is that actually going to reveal any insight into the problem? And it's not clear, maybe for most of you right now, how that's going to happen, but magically it is going to happen as we do this. So we'll follow along and see how that happens. But at first, our only goal is just to somehow come up with a more manageable way to juggle this huge matrix. So our two smaller matrices, we're going to call them a user and a product matrix here. And right away, that might be suggestive of the direction that we're heading in. What we're going to do is we're going to reduce this original matrix here, we're going to call R, into a user and a product matrix whose width and height is up to us to select. So we're going to figure out how much compression is going to go on here. Now, as we smooth this out, as we compress these matrices here into these smaller ones, it's going to smooth out our data points here and smear them out so that where we originally had mostly zeros in this R matrix, we're going to start to find values get filled in. You can think of this, not inaccurately, as it's like we're taking a JPEG image of a starry sky at night. And you know, if you take a JPEG and you keep increasing the compression, it smears things out, right? It's unable to reproduce faithfully the original image. You can imagine if you took a JPEG image of the stars at night, that it would go from being crystal clear, maybe in the original raw image with high resolution, it's very sharp. And as that image gets smeary, the stars are going to smear out from being singular points, right? That's exactly what we would all expect to happen as we increase the compression on an image that maybe we've even just got stored there. We took a nice, crisp, high resolution image of the sky, and we're compressing it more and more with JPEG to get it to fit into a smaller space. It's going to get smearier and smearier, and the stars are going to get smeared out. That's exactly what's going to happen with our data points from our R matrix as we can keep trying to compress them into these smaller U and P matrices here by picking a smaller value of K here. What we're going to end up with is the zeros being smeared into, and you might, again, intuitively, it seems like that's nothing but bad. It's an inevitable trade-off for compression. But amazingly, we're going to find out that those smeared out zeros start to give us valid projections for the movies that the user hasn't seen. And we'll look at some of the magic behind that, but that should be startling, I think, to most of you, that actually, this lossy compression scheme that we're forced into just by the size of the matrix is going to also give us the results that we're looking for. Okay, so, and once again, why are we getting this 2 for 1? And one way that yesterday I told you can think about learning is really compressing a representation of the world of your data into a smaller representation. And I gave us a couple perspectives on that yesterday with some of the approaches we looked at, and we'll have a lot more this afternoon. But this compression idea is universal to machine learning. And it's a very fundamental and very useful perspective to have as you pursue particular algorithms to solve problems. Now, again, this should not be that surprising to you as a human being. This is something you can do as well. Let's say you worked again in that video store, but let's say this time, you've never even heard of Steven Spielberg. So we don't even know, you're not even a knowledgeable clerk in terms of directors, but you did pay attention to what people are renting. And so you did notice that somebody that rented E.T. and Raiders of the Lost Ark and Jaws and Close Encounters liked Jurassic Park. So if you have a customer that comes in and really enjoyed an Indiana Jones movie, you might be able to suggest to them that they might also like Jurassic Park. You don't even know who the director is. So in this case here, that latent effect, you don't even have to be consciously aware of. You just notice this commonality between customers, that the customers who like this one set of movies also seem to enjoy this other movie. So you as a clerk are uncovering latent effects, and again, without even knowing that it is this common director behind the scenes. And again, that could also apply to the actors in movies or genres or release dates. You might notice that all these customers like the same cluster of movies, and they're all 80s movies. People just like these movies from this period. And so you can start to recommend common movies to them without you even being aware of that fact. So this is, again, you're thinking of a reduced way to think of customers. They like 80s movies. These customers like Steven Spielberg. So you're thinking of ways to, and again, we would do that all the time. If we have friends that like movies, somebody says, what kind of movies does your friend like? You might say, oh, she really likes documentaries. right? You're thinking of a way to represent what she likes in a more compressed fashion. If I say, what kind of movies does she like? You don't have to go and tell me every movie you can think of that she's ever seen. And then I have to, oh, those are a lot of documentaries. Instead, you sum it up. She likes documentaries. Oh, and she also likes, movies, French movies with subtitles. And you can sum people up by compressing, their representation down. And again, that's the normal way we think about the world. So this is what's going to happen here. And our K is going to determine how many latent effects we can capture. So that's the magic that's going on here, is we're going to capture for the users and the products some latent effects that summarize what they are. Instead of just having to say for every user, I can remember all the movies they've seen. Instead, we're going to start to capture the latent effects. And again, because of linear algebra, all we need to do is make sure that K and K are the same. And then we can reproduce, we can multiply this row and this column here to get any data point that we want for any row and column in here. But as we make the representation smaller and smaller, we're going to smear things out more and more. And the question might come up, how small can we make K before it just can't reproduce R at all? It's not going to capture the original input data well at all. So how many latent effects are we going to have to incorporate to get some useful information out of here? That's something we're going to have to investigate as we go along. This is called a hyperparameter, a parameter that's up to us to choose to make sure that our model is going to actually be workable. Okay, now as we pursue this idea of compressing our matrix down into these smaller matrices here, we're going to wonder how terrible of a job are we doing? How, as we make the K smaller and smaller, how unfaithful is our representation getting? And so there's an error there that's going to show up. And once again, in machine learning, we're going to find an error is very important to defining, our goal. Yesterday we could see we had an error with our clustering problem, for example. What's the distance from all the points from their clusters as we try to cluster things? Here we have an error problem. We're going to try to figure out how good our data matches our original given data. How close are our approximation matrices, U and P, going to reproduce R? And so we need to define an error. And defining an error, as I said yesterday, often has multiple choices. And here we could do multiple things. We could use root mean square, for example. We could do we could do a number of different things. And so you have multiple choices. As I said yesterday, sometimes multiple choices will work, and it comes down to which one will work the best. And sometimes it's difficult to even make a choice. For example, if we're doing image recognition and we're trying to tag pictures, this is something we're going to do this afternoon, and we try to tag pictures as a cat or a dog, well, we've got a bunch of animals that we might tag the pictures as. And so what happens if we tag a picture of a dog as a horse? Or say it's got lots of objects. What happens if we tag it as a car and we're really far off? How do you quantify? What kind of error number will we associate with this, missing the target, so to speak? And so we're going to find that defining the error isn't always obvious, and it's often we have multiple choices. And in our case right now, what we're going to do is we're going to take the mean square error distance of each one of the matrix elements and add them all together. So we're going to go element by element through our matrix and see how far off we are. And that will give us some feedback as we try to figure out how small we can get with K and our U and P matrices here. And so this is what our error term is going to look like. And this is the standard terminology saying element by element. So we're going to go through element by element and take R, each element of R, and find the difference between it and the element that we would reproduce by multiplying our U and P matrices to get that element. And then we're going to take the square of that. So this is pretty simple and straightforward, and it gives us a nice error back that's going to give us some idea of how far we're missing with the matrix. Now we're also going to find ourselves running into the same problem that we had yesterday with our clustering, where we said with our clustering we could easily go to, we had 5,000 points yesterday, our clustering problem. I said, what if we find 5,000 cluster centers? Then we're driving the error to zero, but that's ridiculous. It's not giving us any information about clusters whatsoever. So we could have continued just to driving our error to zero and learning nothing. As a matter of fact, less than learning nothing, losing information. And that overfitting problem, I didn't use that term yesterday, but I'm going to use it today, and you're going to hear it an awful lot in machine learning as you go through it. It's a major problem. It's one of the foremost problems you're going to run into for almost any kind of real machine learning you're going to do. That overfitting problem is one we want to avoid. And we can also run into that here. In this case here, our overfitting happens in a slightly different way. As we make our U and P matrices a better and better fit to our R matrix here, what can happen is we can have some very large spiky elements start to show up in our U and P matrix. And so in an attempt to reproduce these singular points that were floating around R, our U and P matrix start having elements that go to negative 5 million and positive 480. And we might think that that's intuitively unreasonable, and we would like those to kind of come back and represent star ratings from 0 to 5. So we might find these very large elements aren't desirable for that reason. And so we want to penalize large elements driving that are trying to compensate as we get smaller and smaller values of K. So how can we penalize them? Well, let's do the obvious thing. Let's just penalize them by some lambda that we're going to multiply times their size. And so that's what we're going to do. And once again, we're going to come back and discuss again how this too little error, can be a problem, but it's the same as clustering yesterday. And so we don't want to just say we're going to drive the error down at the expense of any other weird effect that might happen. In this case, the weird effect would be we get some very large spiky elements in our U and P matrices here. So this overfitting idea, extremely important. Let's give what I think is the archetype example of it that we could explain to anybody that's taking geometry and algebra in middle school and they're learning how to fit curves. Maybe they're doing a science experiment at the time. So they're doing a science experiment and they're discovering some quadratic effect in nature. Nature's full of all kinds of things that happen, second quadratic type of curves. So they're plotting some data out from experiment and it looks like this. Okay, well, we might intuitively predict that this is the kind of effect that we're finding here. And so we might say, this is the kind of curve that we want to fit here, a second order curve to our data. But at the same time, they're taking their geometry and algebra, basic algebra, and they're learning that you can fit 5 data points with a fourth order curve. Always, you can fit it perfectly. So, that's when you're fitting curves, right? You can fit any 2 points with a line. You can fit 3 points with a second order curve perfectly, right? Well, if you give me any 5 points, I can come up with a fourth order curve that hits every one of those data points on the nose. That's simple algebra, right? And so because they're clever and smart and they learned that week, they said, I'm not going to tolerate this error that you have here with your second order curve. We're going to fit this with a fourth order curve. And when I fit this with a fourth order curve, this is what I get. And I've hit every data point. I've driven the error to 0. Okay, well, is this a win? Well, you might start to be a little bit suspicious if you know kind of the phenomena you're investigating. Yeah, or even if you just know the general principle, Occam's razor, you might say, well, this is a much more complex, hypothesis here. Do we really want to do this just to get that last little bit of error squeezed out of our problem? And the answer is probably not. You probably haven't discovered a law of nature that looks like this. You might even be able to rule it out because, for example, you might find that negative values are physically impossible or something like that. But you'd certainly probably be skeptical that this is actually an improved hypothesis here. But yet you've driven the error to 0. So just like yesterday with our clustering problem, when we could drive the error to 0 with 5,000 data points, we find we can drive our error to 0 here just by going with the fourth order curve, and we probably are doing the wrong thing. So we'd like to penalize, in this case, if you were finding fundamental laws like this, you'd probably want to penalize higher order polynomials. You wouldn't want to rule them out, but you'd probably want to say every higher order polynomial needs to be penalized with some kind of higher error term, and that would probably suffice here and help you to find the appropriate curve. In our case, what we want to do is come up with that regularization parameter from that previous slide. So that introduces yet another term, regularization. And regularization is an attempt to fight off this finding higher, driving error to 0 in an appropriate manner. So we could figure out if we're doing the wrong thing by grabbing some more data points. If we're doing our experiment here and we think that this was the right thing to do, what we could do is do some more experiments, and we'd probably find that actually our curve, our second order curve, really would kind of look like this, and this would give us a clue that we're going in the wrong direction. So we have there's a method for us to figure out that we're going in the wrong direction and we're overfitting, and we're gonna help ourselves to do that. But the regularization parameter is what's going to enable us to do that here. In this case here, I said we might want to penalize higher order curves. In our movie case here, what we want to do is penalize large elements. So this is our regularization parameter here, this lambda. So again, anytime you're in machine learning and you're thinking about overfitting, I think this is maybe a good touchstone here. Come back to this example here in your head and think, yeah, I kind of get this. I get that driving error to 0 is going to come with a cost. So this is going to help our problem to generalize well. This is another term that you'll hear an awful lot in machine learning. It means basically after you're done training and you go expose this to the real world, to new data, is it going to fit that new data? This model won't generalize well with this higher order curve, right? When the new data comes along, it's not going to fit. Our previous curve, simpler, even though it had more error, is going to generalize better. So even though it had more error, it generalizes better. This one has lower error, but generalizes in a worse way. Okay, so let's do that here. So here's what our new error is going to look like as we try to fit our U and P matrices, come up with good ones. Here's our feedback. Here's our error that tells us whether we're going in the right direction. It's going to basically be the difference between all the elements plus this penalty here for these large spiky elements. So in other words, we're going to go through the matrix element by element here and just take for each element of R, we're going to subtract the element we could generate by multiplying our U and P matrices here. And that's going to give us our baseline error. And then we're going to have our penalty here with our regularization parameter that we're going to add in there too. So this is now, by the way, we've also got another hyperparameter that I didn't call it that when we introduced, or maybe I did call it that when I introduced it, K, a hyperparameter. So we've got two hyperparameters here. I think I did mention it's our first hyperparameter. Now we have two hyperparameters in our model, two things that we've got to come up with reasonable values for if we want our model to work well. So you can see hyperparameters start to creep into our problem, things that we've got to determine that make our going to, even though we've already picked our algorithm that we're going to use here, and even though we've come up with an error term, we're still going to have to fight around with these hyperparameters to minimize, and get our model to work well. Okay, the actual method we're going to use to get our U and P matrices to approximate our R matrix, though, is going to be alternating least squares. So far, I've avoided that discussion. You might have said, okay, how do you get these U and P matrices to even work? Well, given R, that's our data set. We're reading it off disk. It's a bunch of data points. And I've said we're going to get these U and P matrices that we're going to be able to squeeze them down with that K. But how do we even do that, though? How do we come up with an approximation? And if you sit down and write out all the equations to try to fit these matrices here, it starts to at first seem, especially for a large matrix, like an untractable problem once again. But we're going to come up with a kind of a cheat here, alternating least squares, that actually works. And alternating least squares kind of treats this like a much simpler problem, a linear regression problem, to fit these matrices or come up with the approximate matrices here. Well, I'll explain to you briefly how it works. We're going to treat it as a black box largely that Spark can provide for us. So you don't need to know the details, but it's not that complicated, so I can't explain it here. Alternating least squares basically says we're given R. That's our real matrix we're going to fit. So U and P are both unknown matrices. If we try to just come up with those, the best fits straight up with U and P both being unknown, it would again result in a lot of complex equations, very difficult to fit, impossible to fit. But what if we pretended that U was already fixed? We had a good U matrix. If somebody handed you R and U, then fitting P to it is not a difficult problem. If you multiply all those elements out, then you're given a bunch of simultaneous linear equations, and it's not difficult to fit that. So if somebody gave you R and U and said, come up with a P that fits this, you could do it. It wouldn't be hard. It'd be straightforward, again, on high school level kind of algebra problem. But we're not given U or P. So what if we instead pretend we have U? Let's fill it in with some random values to start with. So we fill in U with some random values, and then we find a P that fits. Okay, well, what does that do for us? Well, if we then take and pretend that P is a good P, and we find a U that fits, that also is a simple problem. Somebody handed you R and U, you could fit R and P, you could fit U. So then we find a U that fits. Okay, let's alternate that process back and forth. And what we would find is that for anything that's not a weird pathological case, that indeed U and P would eventually home in on a pretty good approximation. So that's alternating least squares. We do a standard least squares fit that, again, is a very doable, simple problem. But by alternating back and forth between U and P, pretending that we, starting with random values and then pretending that they're good values, we can come up with a solution. So this is the way we're going to do it. This is easily parallelized. That's one of the reasons it's very desirable. Again, in this day and age, anything that's parallelized is a huge win, not only because Spark is going to do everything in parallel behind the scenes, but all modern computing equipment depends pretty much on you being able to use it in parallel to do things effectively, even your laptop. So this is a hugely desirable feature. It also works well with sparse inputs. We might think of some other ways we could do this, like, for example, SGD, up here is well, actually, I was going to say SVP, separating this into a different decomposition. There's lots of different ways we could attack this problem. And you might, so if you have any experience in this, you might come up with a number of them right off the top of your head. But this one is the only one you're going to find that works for huge matrices. So it can run in parallel, can fit into memory well because it takes advantage of the fact it's a sparse matrix. So we're not at any point in time keeping the entire matrix in memory. So that's the reason this fits particularly well. Okay, but again, there's lots of alternatives and that you might think of. Ask yourself though if they would work at that scale and in parallel and with sparse matrices. Here's our general plan as we've kind of formulated these pieces. So we're given this sparse R matrix here. And so again, if we want to think of it in a tabular form, down here, this is what we're given. We're given this sparse matrix. We know we'd like to fill in all the values so we can predict for any user any given movie that they might be interested in. So we're given this, we want to end up with that. We're going to do it by coming up with these U and P matrices here. So that we multiply any given row by any given column here, we're going to come up with a new element, even one that's missing. So we want to find this missing element here, right? And it's in this row and column. We just come over here and we get the right row, and we get the right column, and we can reproduce that element. So that's our goal, is to come up with good U and P matrices here. And they're also going to have the virtue that our U and P matrices are going to be much smaller. So keeping them around in memory. Once we've solved this problem, we've got great U and P matrices. We never have to keep any large matrix around in reality. We can pretend we have this large filled in dense matrix. But all we actually have sitting around behind the scenes is a smaller U and P matrix. And anytime we want an element, so if we want this element down here that didn't have any user data, but we want this element down here, we don't have to have the whole array, dense array sitting around. We can just go and multiply out this row and this column and get this element down here. So that's another virtue here. It's going to be much more tractable and manageable. We can keep a smaller data set around, but we also hope at the same time that it smears out and gives us these new values, right? We're getting very much 2 for 1 here. So we hope that we end up with this matrix from this matrix by this approximation matrix here. Okay, that's our plan. Now, to do this, we need to take our original data and come up with our U and P matrix. And so you might think the obvious thing to do is just take all of our data and throw it into the mix and start coming up with the best possible U and P. But what we'll find out is that we might end up overfitting our data here, because even though we have this lambda, we don't know what the right value for lambda is, right? We haven't figured out the value, and there's no way to do that on paper. So how do we know that we're not overfitting? Well, the only way to know that you're not overfitting is to keep some of that data squirreled away to the side so that you can go back and check after the fact and see if your problem generalizes, right? It's like with our curve. We had 5 data points and we generated a couple of curves, one of which was kind of squirrely and complex and didn't fit. And we could figure that out by bringing in another 2 or 3 data points to see, oh, these data points this curve doesn't generalize well. We're going to do the same thing here. So we're not going to use all of our data for training data. Instead, we're going to set some of our data aside to check after the fact and see if we're doing a good job generalizing, to validate if we're coming up with good hyperparameters like lambda and k. So we're going to set a slice of our data aside as validation data, and that's going to help us to prevent from overfitting. And that's exactly the right approach. The only problem with that, though, is that you might even pick lambda and k values that are still enabling your overfitting. You can't really be sure that you haven't somehow, as you've wandered through your lambda and k hyperparameters and all the other hyperparameters that might come into play, you might have had hyperparameters that really are helping you to overfit the training data as well. The only way you can really be sure that how good your model is performing is that you set aside some data at the very beginning, you set aside some test data that you never use for any of this process. It never enters into your model development process. That test data, which you set off to the side, is the only data you can really trust to be independent of this process and to give you a good quantitative result as to how well your solution is working. In other words, the test data has to be sliced off at the beginning, never used in the development process at all, including coming up with hyperparameters, and only used at the very end to judge your solution and any other and all other possible solutions, hyperparameter combinations or anything else. In the Netflix competition, the real test data was kept by Netflix. You never got to see it. So that's what the judges used. I shouldn't even call them judges because it's a quantitative thing. So the real data was kept back at Netflix. the test data was kept back at Netflix, you never got to see it. It was hidden data points that they could use to judge everybody's entries. It gave them a very quantitative, objective way to judge entries, to judge all of it, to see who got the $1 million. Was they said, we're not even releasing part of the test of the data, the user data to you. And when you all come up with your different models and different approaches and different combinations of hyperparameters or whatever you do, when you submit your solutions to us, we use the test data to see how well you really generalized. So you never even get to see the test data. So keep that in your head if you want to get a good idea of how isolated the test data really has to be, is that in a serious competition, it would never even be given to you at all. You'd have kind of slice off your own test data to use along the way to develop things. So we have, three kind of pieces of data here that we should use in the process. Our training data are used to create the UNP matrix. Our validation data can be used after we train for a particular set of hyperparameters to go back and check those hyperparameters. And so we go, oh, let's see, this lambda, I think this is pretty good, but can we do better? Let's try a different value of lambda. We use the same training data, a new value of lambda, and we go back and check it against the validation data to see if we have a better lambda. And we can do this as much as we want. We can recycle this guilt-free. And at the end, when you finally think you know what you're doing, and only at the end, when you're done and you're ready to deliver the model, do you try it against the test data. And that gives you the real judge of how well things are working. And reusing any of these things or mixing them up is frequently a serious cause of confusion. And the reason people do this is because, and we'll see this as we really get into the deep learning stuff this afternoon, is that data can be very valuable and hard to get and expensive. And so people really want to use all the data to get the best, UNP matrix, to train their model as best as possible. It's a huge temptation. Setting aside some of your data that never gets to be used to make a good UNP matrix is painful to do, especially if you don't think you have enough data to begin with. You really want to be stingy with your data. And this data never gets to be used to train the UNP matrix to be better. That's a painful thing to do. So people just have this temptation to reuse the data somehow or other and mix it in. And it's a big problem more often than you think. But this is what you should do, is you should slice off the test data at the beginning, is what we'll do, and never use it. Now, there are techniques that you can use to try to slice and dice and cycle between the training data and the validation data, so that some of the validation data you can use to make the UNP matrix better. And it gets a little bit sophisticated. Cross-validation is the most common version of this, but you still never, ever want to let the test data enter into this process. I see this happen a lot. People think cross-validation is an excuse and a license to use the test data and cycle that in, and that's not true. So this is not that fancy of a thing, but it's not something we'll dive into today either. So now, what proportions of your data do you want to use? That's the obvious question that comes up. And the answer is, once again, this is a hyperparameter that doesn't have a set answer. So, it's the obvious thing. As soon as you start to do this problem, you say, okay, now how much of my data should I set aside for my training data, my validation data, and my test data? How should I divide those up? And there is no set answer. And again, it's not an easy thing either, because the more test data you have, the less it's going to be used to come up with a good UNP matrix. But if you don't have enough test data, maybe you won't be able to detect if you're really generalizing well. So it's one of those things where there's just rules of thumb in different areas and different domains. And your best guess is probably to look at what similar people are doing in similar circumstances. In our case, we're going to break things up. We're going to save 20% of it off to the side for test data. But it's not, there isn't a definitive answer, and there isn't one that, that you can apply to all problems. So again, our training data is going to let us generate different curves here, and our test data is going to be the reality check. And if we make a mistake and we use our test data, we can end up with an even worse problem. So this is going to be, for our first pass, our validation data is going to let us find better and better values of lambda, is by setting this data off to the side. And we're going to use that, and we're going to come up with a good value of lambda, which is going to give us a good curve. But at the very, very end, after we're convinced that this maybe simpler curve is the right answer, that at the very end, when we're all done, is when we can finally use the test data to bring in a few more additional points, and make sure we're not doing this by accidentally using our test data too early in the process. By the way, another way that this can be expressed is with these similar concepts. And we can also say that this model has, this model here, this bad one here that doesn't generalize well, this model has a very low bias, so it fits the data well. That's a low bias, but a very high variance because it doesn't generalize well. So those are two other common terms that you'll see to express the same concept, and it's getting at the same idea. Okay, so here is where our data is going to come into play. We're going to take our matrix, or take our data set from the disk, the disk file that we've got sitting around, the given ratings data, And we're going to take right away, slice this into 3 pieces. They're not equal sized pieces, but we'll see what we're going to guess that we might use 60% and 20% and 20%, 60% going to training data. That's our first attempt at dividing the data up. And then we're going to use that data to train the training data, that is, to train the U and the P matrices here. And then when we train those on a particular value of K, for example, here, we're going to use the validation data to see how well that value of K worked out. And we might say that didn't work very well. We seem to have a very large error here. Let's try a different value of K. And we can go back and we can do this as much as we want. We can keep reusing this validation data to help us find a better value of K or lambda or any other hyperparameters. We'll see a few more work their way into this problem even. And we can do this as much as we want. And that's all good as long as our test data never gets involved and pollutes this process. Our test data at the very end, when we're done, when you walk up, this is what we're going to submit for the competition, that's when you can actually apply against the test data. Or if you're working for the boss at some company coming up at Netflix and you say, hey, boss, we got our better Netflix recommender algorithm. When you finally walk into the CEO's office, this is when the test data gets applied to see if you really did do a better job. Let's go ahead and do this now. Let's take our Spark tool from yesterday, fire up our PySpark shell, and I'm saying this metaphorically. Please don't follow along with me unless you feel really, really comfortable. Instead, I suggest you sit back and pay attention. You can follow along, but again, I suggest you don't. We have exercise time after this and lots of exercises and extensions to this problem to pursue, so you probably don't want to follow in real time. So we're going to load and parse the data files. We know Spark's good at loading in big data set and even cleaning up if we had noise and mess and everything in our data we don't hear, but very often you would. Then we're going to create our alternating least squares model. We're going to find that's very simple. It's a nice tool in the toolbox. We can treat it as a black box, as a matter of fact. And then we're going to try to find, in our case, we're going to do a hyperparameter search. We're going to try to find the best value of K here, one of several hyperparameters involved, but for our first pass, it's the only one we're going to try to find. And then once we think we got a working system, we're going to add a new user in and get some recommendations for that user because we're going to try, build a real application here. So again, if you're following along, but this is mostly for reference later. This is for after I'm done talking. That's when you probably want to do this. If you recall from yesterday, after you log in, grab an interactive node, load the Spark module, fire up your PySpark shell, and then here we would be. So once we're in PySpark, we want to read in the data set. And as per yesterday, Spark makes it very simple to read in a text file. And these are just comma separated text file here. We're going to read it in and we're going to find ourselves with an RDD that we're going to want to massage a little bit because it's a bunch of text information. And just like yesterday, we want to then split things up and convert it into integers because we're going to be working with all integers, actually floating point numbers for our ratings here, integers for our users and our movies, and floating point numbers for our movie ratings. So right away, we're just going to want to read things in and convert them. And that's very easy to do. As a matter of fact, if I want to check, I want to check that I'm doing the right thing. After I read things in, I can look at what I've got here. So after I convert things down to my training RDD, I can take a few of them. So I don't have this in our muddying up the screen here as I work through the example, but I recommend that you, as you work through things, absolutely take a few elements here and there as you step through this and make sure you're doing the right thing. So I take a few elements and make sure I've got what I think I have here, which in this case here, this is user number 1, saw movie 1029 and gave it a 3-star rating. So that's pretty much what I hoped for. But the way I've divided things up here is after I finally, I got the data into the right format like this, I want to divide it into 3 pieces. So I have my training data, my validation data, my test data. And so I can use a nice random split routine built into Spark. It has all of these features that you would expect to utilize in machine learning are at your fingertips, of course, for your convenience. So random split's one of those. And by the way, when you split your data up, you want it to be random. Very often it's the case that your data set might have some kind of correlation, time correlation or something in it. So you want to make sure when you split things up, it's random. And we don't even have to worry about that here with our random split. I think our data set, for example, if you look it in, I think it's sorted mostly kind of by users, user 1, user 2, and you wouldn't want all your training data to be some set of users. And so instead we want random data. So we grab a bunch of random points and this will split it up into proportions of 3, 1, and 1. So again, you might say, where did those come from? That's my best guess to start with. I saw that somebody else used roughly these proportions, so I grabbed them. And that in general is the theme of hyperparameters. We'll come back to that as we have more and more hyperparameters, is you take your best guess based on what somebody else is doing in the most closely related problem you can find, and you test your way and work your way from there. That's how you find hyperparameters. Okay, In our case here, we split our data up here. Now we've got our validation and our prediction RDDs. And as a matter of fact, when we go back later on to compare against this, if we want to predict, so these are some, so our validation RDD, for example, are data points that we were given from R, and we know that these users actually have given star ratings. But when we go back later on, we want to look for those. We're going to strip out the star rating and see if we can find the right value. So for our prediction RDDs and our for both the validation and the test prediction RDDs, we're going to drop the rating. This last floating point number, we're going to drop it off of them. So later on, we can ask the system for them. We can say, hey, give me for user 1, give me movie 1129. And then we know that this was actually given to us originally in the ratings RDD. We can go back and see if it gives us the right value. So that's why we're dropping the data off the end, the rating data off the end for our prediction versions of the RDDs, because these are the ones we're going to ask the system to predict for us later on and check our error. We want to make sure it predicts ones that we actually do have data for. It'll predict new movies too. I mean, the whole point of our recommender system is we're going to predict any movie for user 1. But we want to make sure we have some to check on and we can predict that we have real data for, so we can see how well we're doing. So that's why our prediction ones we're dropping the floating point number off the end. Okay, so we got our data, our RDDs set up to use here as we come down here and do our machinations later on. So now it's time to jump into to using ALS. So we load our mlib version of ALS here. And again, it's got multiple algorithms here for recommendation, but we're going to use ALS. And we set up some hyperparameters that we're about to use. And if we look, again, the documentation on this that we had from yesterday is excellent on this. So I'm referring you to the same Spark documentation link that we used yesterday and I have in our exercise slide. And it's great, and it lists all the parameters that are part of ALS, but the ones that we're going to set up in advance here, first one is seed. And once again, as I said yesterday, we find ourselves dealing with random numbers an awful lot, with machine learning. We think things are deterministic. We want to just recommend movies for users based on given data, but we immediately find ourselves having to do some random stuff. What's our random stuff here? Well, if you think back when I said ALS has to initialize our UNP matrices to even get things off the ground. We can't start with all zeros. If we had all zeros in our UNP matrix, ALS couldn't bootstrap itself. It wouldn't be able to do anything. So our UNP matrices to start ALS off are initialized to some random values, not good values, but just random values. But you can imagine those random values ultimately might have some effect. We hope after it homes in on the approximate good matrices that it's a minimal effect, but we can't be sure, and it's certainly some effect. So we need to initialize those things randomly. So we're going to give it a random number to control, repeatedly how we initialize those things and see if we're sensitive to it maybe. So random numbers, again, keep cropping up all the time in our machine learning. And we have to be aware of that, because if we were to later on say change the seed and a slightly different random number caused our results to vary a whole lot, we have a problem. We have some instability here in the way things are converging or whatever, and we can't ignore it. So we hope it's not important what random number we pick, but we better pay attention. Okay, a second parameter here is number of iterations. How many times does ALS go back and forth in homing in on the correct UNP matrix here? Well, that's up to us to pick, and I'm going to pick 10. And again, you might say, where did that come from? Well, maybe I saw somebody else thought that 10 is a good starting point for ALS, but it is once again another hyperparameter. It is another parameter that we have to pick that's going to determine the success of our model, and we should investigate whether it's the right one. It'll be part of our homework problem here, but we're going to pick 10 and hope it works well. The next hyperparameter is our lambda, our regularization parameter. Can't call it lambda here because that's a keyword right in Python here that we've been using. So I have to call it regularization here. So our regularization parameter, our value of lambda is going to be 0.1. And once again, same thing with the hyperparameter. Where did I get that from? Well, I saw somebody said start, maybe a lambda value of 0.1 is okay. Okay, well, I'm going to try. It may or may not be the best one, and we should investigate that. But the one we are going to actually investigate right here and right now is going to be our value of k. And I'll call that trial ranks here, but this is our k value right here. We're going to try 3 different values of k, 4, 8, and 12. They're going to determine how wide and tall our UNP matrices are and how accurately they can fit our R matrix. So this is the hyperparameter we're going to investigate. But these other hyperparameters here all bear investigation, part of our homework problem. So we're going to hope that our initial values, our initial guesses will work well enough. And indeed, as you might guess, they are somewhat informed guesses, so they'll work pretty well. but they definitely, you can't take it for granted. But our K value we're going to find. Okay, so we got some parameters here that we're going to feed into ALS. Let's go ahead and get started. So here is our 3 trials of K that we're going to try. So that's what this loop does. It tries a K value of 4, 8, and 12 on our model. And all the magic is really here in the first line. The rest of this stuff here is just some simple math exercise in Spark juggling, and we'll step through it line by line, fear not. But here's where the real magic happens here, which is to actually use ALS to train the model. And so what do we give it? We give it our training RDD. So this is our training data that we broke out. We gave it our K, our ranks to use right here. We gave it a random number seed. We gave it the number of iterations to use going back and forth, and we gave it our lambda for regularization. So this is really all the magic. After we do this line right here, we hope that we have in our model, hidden behind our model, we hope we have a good U and P matrix trained at that point that we can use to make some predictions. So that's what happens in this line right here. We say, go and use ALS, 10 times back and forth with this lambda, initialize with this seed and with U and P matrices that are 4, 8, or 12 wide, and train the model, come up with those U and P matrices. Okay, so that's what happens. Now, let's look at the rest of this math here. Not because it's actually super interesting, it's not, but it is a good example of the mechanics of Spark from yesterday that we want to make sure everybody understands. So here's the mechanics that happen after we train the model. What we want to do is we want to get our data, our RDDs. We want to do everything in RDDs. Again, the theme of Spark, keep everything in RDDs, and it will all happen very scalable and very parallel behind the scenes. So we don't want anything to be some Python variables, local Python variables we're juggling. All this stuff takes place in RDDs, and so it'll be very fast and efficient, even as this problem grows to be enormous, the full Netflix competition problem. So I get back from my training model, I get back this. If I look at my model, actually, if I take my first couple RDDs from my model, this is what I've actually got. It's giving me back a bunch of user product rating combinations. It tells me that user number 463 would like movie 4844. We're going to predict 2.76 stars. So this is what comes back from our trained model. And that's pretty much what we'd expect, what we hope for. But what I want to do is to see if our value of K is good, we want to find our error. And we defined our error earlier. We said an error that we're going to like is to go element by element and look at the root mean square difference. So what I'd like to have at the end to compare things is I'd like to have for every single user and movie that we have in our predictions RDD. So all the ones, we want to compare the ones we set aside earlier that we set aside for test data. So here's our test data we set aside earlier. We know that we grab the data point 119 and 145. And what I'd like to do is to have at my fingertips to do the math here. I'd like to have the actual rating that they gave us in that data set, 4 stars. And I'd like to compare that against what our new ALS model is predicting for them, 2.9 stars. So for this one element right here, I can see what my error is going to be, right? I want to take the root mean square difference between these two right here. And I want to do that for all the points that we set aside in our predicted RDD, right? So this is what I'd like to have, and this is where we're starting. So it's no big deal. I'm just juggling some data points around, but let's step through this process here because it'll illustrate how Spark works that we did yesterday. So I hope you can follow through with me on this. It's boring again from the profound machine learning sense, but it's very useful to make sure you understand how Spark works. And it also will show us once again how these joins, I mentioned to you yesterday, joins keep popping up. So once again, we can see a join pop up right here. So let's step through this. I want to get from here to here. And how do I do it? How do I get from this model right here down to here, right? So I can do this math that I want. Well, let's step through it. Okay, first thing I do is I map the values that come back that were given from the model. I want to do a mapping here. So I do a map to massage them into a little bit closer form. So I map them into user, movie as my first element here. And then here's the rating. And why am I doing this? Because this is getting me closer to my final result, and it makes the user and the movie a key. What have I magically ended up with? I mean, I'm not trying to do it. It's just happening by itself. I ended up with a key value pair. It turns out my elements are a key value pair. I'm going to get a pair RDD. If you remember the terminology the Spark world likes to use, if you want to remember pair RDD, doesn't matter. I just think of it as a key value element. I've now got an RDD that's a bunch of key values. My key is the user movie combination, and my value is the rating. And I just did that by doing this little map right here, right? So I mapped the values. I just pushed them around a little bit to make a tuple. The first element is this combination of movie and user. And the second element is the movie rating, right? So I'm just massaging the data a little bit, but it's putting me in the right direction. And again, there's nothing really interesting from a machine learning perspective, but I hope you can follow along and understand how to use Spark to make these kind of manipulations simple and straightforward. So I massaged the data a little bit in the right direction. Now I want to do the same thing with the validation data, because the validation data that we set aside, right? We're using the validation data to find a good value of K. That's its job. Validation data we set aside to help us find good hyperparameters. And the validation data that we set aside, we want it, look like this: user movie rating. And we want to massage it into the right form of user, movie, and then rating. That gives us the user movie key and then the rating value. So that we're going to have the keys in all of our pair RDDs be user movie combinations, and the values will be the movie ratings. And once we do that, so that's all we're doing here. That's all these maps are doing. And again, please step through it and make sure it makes sense to you. You understand the mechanics of it, because they're not interesting, but they're basic. And once we've done that, now we find ourselves with a couple pair RDDs, and we want to somehow combine them. And again, if you never heard of join before, you'd still want to find yourself doing exactly that. You want to say, I want to find all the common key value pairs between these two and combine them. And I want to throw out all of the data that there isn't a common key value pair, right? The movie predictions could be a lot of things that we didn't have, we didn't set aside in the validation data set. So this is going to grab just a validation data set, and it's going to pull all the ones aside that we have common predicted ratings and common given ratings, star ratings from the user. And so we do the join, and boom, there we are. Now we've got our data in the form we wanted to perform the math on. So like I said, I just spent 3 or 4 minutes painfully talking your way through some simple mapping and join commands in Spark that I hope are starting to seem boring to you. I hope it's boring to you. If it's not boring to you and it's still confusing to you, pick through your way through this step by step, because you want to get comfortable with this if you really want to be good at juggling data. It should become boring to you. And if it was boring to you, then you can at least see that, hey, we got ourselves down here to where we can do this simple math on this, which is just take the difference between, the star given rating, the predicted rating. We square the difference. We take the mean and we take the square root of that. Boom, root mean square. That's all this line is here. And then we can finally print out our error. So I hope this was just some boring data juggling to get some math. So I think at this point in time, we've stepped through one of the Ks here to generate, to find the error from, how well the model fits our validation data points. And for 4, it turns out to be 0.93 stars. And then we go through again and do the same thing with 8 and with 12. And so this is how we're investigating this K hyperparameter here. And we do this and we find that, well, I guess we'll stick with this. We find that our best value of K here is 4. We have the smallest value. They're all pretty close here, but the best value of K is 4. Now that right away initially surprised me a little bit. I'm like, whoa, really? K already seems kind of small to begin with, given the size of our matrices. And then the smallest value of K is the best error. Well, that's what it's telling us. And there doesn't seem to be a flaw in our process here. So we got to go with this. We got to trust with this. However, I'm still suspicious. It seems like intuitively larger values of K, they should be more expensive. So we don't like them for that reason, but they should give us kind of a lower error. And the answer is, yeah, in general, that's true. And part of this is because at the moment, we're only using the small data set. As I said to you, we have two sizes of data sets here. We have the small one, which is very fast for you to compute, only takes a few seconds to do things here and there. And we have the actual competition one, which takes some minutes to chug away. And so it's a lot less fun when you're trying to work out the problem. If we go back to the competition one, we might find that a larger value of K is actually more helpful. So it's not this very small problem here. These results are all pretty close, and we'll roll with this K equal to 4, even though, again, it offends the intuition a little bit to say the smaller value of K is giving a more accurate result. With the tiny data set we're dealing with here to start with, no, it's tolerable, it's believable. Okay, so we found our best hyperparameter value is K of 4. So we think we're done. We think we got a working model. We're ready to go knock on a boss's door and say, hey, let's submit this and win a prize. Well, the boss says, hey, here's the test data, the real test data. So let's do the exact same process here, nothing different, except that now we're using the test RDD. So this data was never entered into finding the best value of K or possibly iterations or lambda or anything else. We found all our hyperparameters. We did everything we could do to come up with the best possible model. We think we got a winner. Let's see how much of a winner we have. Let's see what our score would be when we actually submitted this to Netflix. And all we need to do now is to swap in our test data that we had sitting aside waiting for us the whole time. We do that, and we find out that indeed our error here is about 0.94 stars. Okay, that's not terrible for, again, a small data set and everything else. So we think we got a working model now. We think we're ready to go ahead and release this to production. So let's look at this actually as let's add a few niceties in here to the end, mostly as an exercise in Spark, so you can see how that works. Also to eliminate a few limitations of this particular model and approach. So let's go ahead and roll this out to production. Let's put it on the website. So we want to add a new user. So let's make a new user 0 here. And by the way, I wasn't sure if there was a user 0, so I I just went through the RDD and said, hey, is there any user that's equal to 0? And I found, nope, okay. No user equal to 0. I'm going to make a new user called 0 here. So new user 0. I made up 10 movie ratings for user 0. So user 0 liked movie 100, which happened to be City Hall, 4 stars. Did not like Forget Paris, gave it 1 star. So I made up some ratings for our new user, because that's what they're coming to the party with. We need some data to predict something for them. Now we need to add them back in to our model. And this is one of the weaknesses of this particular approach to recommender systems, is that to add a new user in, we have to go back, add them into our new R matrix. And we got to do the whole problem from scratch again. We need to retrain for that new R matrix. So adding a new user is like adding a new row into that R matrix, and it means got to go back and find a new UNP. So we take this user, we want to turn them into a little RDD here, a nice little mini RDD that we can now add into the ratings RDD. So we now add this user in with our other 80,000 users or however many. So we add this new user in here, and now we retrain the model. So again, it's one of the drawbacks of this is we got to retrain everything. Every time a new batch of users comes in, and we will briefly discuss maybe some ways to avoid that and some shortcuts, but at the moment, that's our only route to get a new user in here. So we add in a new user, update, retrain everything. We now think we've got predictions for that user. So let's get some predictions. Only we're going to try to be a little bit nicer here this time and spit out some movie names. We're going to do some nicely formatted output. We're not just going to say, user would like movie 166. Nobody wants to see that. They want to see what movies they'd like, and maybe even pull out the top 10 ratings. So these are some more exercises in Spark. Nothing super interesting, but you should absolutely make sure you understand how this kind of stuff works and get comfortable with it. So what we're going to do is we're going to step through here, and we're going to take and read in the movie file now. So far, we haven't used that movie file, which connects each movie up with its title, the number and the title, the actual text string for the movie. So now we're going to read that in. Read it in. We're going to split it up into 2 pieces here. We're going to take the integer for the movie number, and we're going to leave the string here for the movie name. And now we want to, so we can again predict real actual movies here. So we take all the unrated movies for this user, and this user's unrated movie list is very big because the user hasn't seen most movies. Nobody's seen most movies. So if we look at all the unrated movies for a user, they're going to be pretty much movie 1, movie 2, movie 3, all the movies except for the 10 that we picked out of our 17,000 movies. So the new user unrated movies RDD is going to be most of the movies, and we want to ask for predictions for all of those. So we're going to ask the model to predict for these unrated movies, to predict all the unrated movies. And so that's exactly what happens, and we get back a fairly long list of movies for the user, almost all the movies, and the predicted ratings. And now we want to see some titles and kind of maybe make them, like I said, a little bit nicer output here. So all we're doing here is we're joining up the ratings with the movies RDD. I'll highlight some of the operations here below so you can see what's going on. So we're taking all the movies and their ratings and their text string, and we actually want to make this a little bit nicer. We'd like to reformat this, and so all we care about is the movie name and its rating, right? We don't really care about the movie number or anything. The user doesn't care about that. So we're just massaging the data a little bit. We find ourselves having to do a join once again, right? To combine our ratings data with the movies information, right? So the movies have the movie product number and the movie title string, and our ratings have the movie product number and the movie rating. So we want to combine those together. Once again, a join pops into the mix. So like I said, joins pop up all the time. You'll find yourself using them. So By the time we're done here, we've massaged the string into the movie name and the number. That's all we really want. If we want the top recommendations, we want to sort this. So we want to take these in order to get the top ones. And so we'll print out the top ones here, and we find out that these are the top rated movies for this particular user. One of the first things you might note is that our star ratings here are kind of off the charts. We'll discuss that in a minute. 6-star ratings. And is it okay to have 6-star ratings? Doesn't Netflix really want to have 1 to 5-star ratings? Yeah, they do. So maybe we should normalize these things back down to a better range. But at the moment, it's predicting 6 stars for Maelstrom and 6.2 stars for King is Alive, etc. Okay, another thing we can do is we can ask for a rating for a particular movie. Do I want to see this movie? So we can take one particular movie and we turn it into a very pathetic small little RDD of one movie. And then we ask for prediction on that one movie. And what comes back is that it says that user 0, the one we care about, would like this movie 800 here that we're looking at, Lone Star, predicts 4.1 stars. So we have ourselves a nice working movie rating system. And by the way, yesterday I said we always want to sort by keys, but I told you, but some of you may have uncovered the sort by value ability, and yeah, you can do that. And so it's hidden in there. And if you look at the actual code behind it in Spark, it actually sorts by keys, then flips the key value pair back, just like we did ourselves yesterday. But that's what we're doing here. So anyway, we now have ourselves a working recommendation system, and it predicts movies. And we've investigated one hyperparameter here, K, but we have some more work left to do. So these are our exercises here that we can start with what we've got and work our way out. For example, the first thing, as I said, was our movie ratings are, should be 1 to 5 stars, right? But they're higher than 5. Now, it's no mystery. So far, we've just been working with floating point numbers. There's nothing in any of our math here or ALS or anything else that says constrain things to 1 to 5 stars, right? It's just a bunch of numbers. And so, of course, some of those numbers started to creep up over 5, which does make sense, right? Because we have, again, there's no ceiling imposed on our algorithm. And so let's say you had a friend that likes anime movies. And so most of her anime movies are rated 5, and she really likes Scarlett Johansson, and she gives those 5s. Well, if you recommended Ghost in the Shell, which is an anime themed movie that has Scarlett Johansson, wouldn't that be the old 7 out of 5 rating, right? As they say on the interwebs. So it's not unreasonable that our algorithm is predicting star ratings that are off the chart, better than 5, better than any movie the person's seen yet. That makes perfect sense. But nevertheless, Netflix does want us to constrain things. And so can you normalize the output so that ratings are back in that 1 to 5 star range in a way that makes sense? This is a good exercise here in a little bit of statistics, a little bit of Spark. We have some other hyperparameters here in the mix that we've kind of ignored and assumed that our guesses were good and valid, but we really should investigate them. An easy one to investigate is that convergence rate. Somebody even asked a question about it already, and we picked 10 iterations. Is that reasonable, or are we wasting our time? And by the way, when you start using the large movie data set, you're going to find yourself wanting to do less iterations. It takes time to chug through these iterations. And so you don't want to be wasteful. But on the other hand, maybe more would give us a better answer too. So when you investigate these hyperparameters, what you basically do for most of them is you graph your results against your hyperparameter. In this case, we've got very simply, we can do a range of iterations and graph the results. And the graph is usually not difficult to interpret. You will see, like I said, the error will be plummeting at some point where you can tell it's really doing useful stuff. And at some point it's going to plateau and you're wasting your time. And we have no idea where 10 is at the moment. We might still, 11 iterations might give us better error. It might give us much better results. Or we might find that at 5 iterations, we were already getting the same results and we can save ourselves some time. So it's a good hyperparameter to investigate. I mentioned that with K, I was surprised that a rank of 4 was giving us our best results. It seems like you should always, higher ranks should be always, more accurate results. As I spoiled a little bit and said, hey, this is an artifact of the smaller training set. If you want to try the large movies training set, which is right there for you to use, give it a shot. Now, the large movies one has the drawback it takes longer to train, so it's no longer a matter of seconds. You can grab yourself a sip of coffee while you're waiting for things to process, but it is more realistic, and this is the one that people trained on for the competition. So you can give that a shot and see if what the best value of K is there, in which case things start to be a little less surprising. Um, and somebody asked about data frames. Well, this is a good chance for those of you that want to play around with data frames to give it a shot and redo this problem with data frames and see. First of all, you'll see it makes things a little bit. There's a little bit more overhead in the code of overhead in the sense of just extra lines of code, and that you've got to make all the data types line up just so. We can't play fast and loose with like we can with RDDs. But that's good, and you'll find that it runs faster as well once things are in data frames. So this is a good time to give the data frames API a shot, and go ahead and port this example and see what you think. Is this a better way to work? Takes a little more effort, but it has some payback. And I think honestly, it also is much more maintainable. I mean, data frames make it very obvious to everybody what things are supposed to be in the code. And so beyond the optimization improvement, which could be considerable, it's just going to be more maintainable. Okay, so that's our exercises. I will answer some questions here in a moment. I'll also point out that today, the Netflix competition would look a lot different, because today, with streaming being their focus on movies today, you'd have maybe all of a sudden some metadata that we didn't use would be really useful. Like, how long did somebody stream a movie? The starting a stream and ending it are two very different things, as we all know, right? If I watched a movie for 3 minutes, I can infer an awful lot about you can infer an awful lot about how much I appreciated that movie, versus if I watch a 2.5 hour movie to the end, right away we can make some guesses about what I thought of the movie. So you can see that modern streaming version of Netflix not only has different data, but also has advanced beyond this algorithm. And these days they typically use, if you can pry out publicly, it's proprietary, and this is very valuable to people, right? So Netflix isn't publishing all the details, but occasionally some of their people give talks. And I saw a talk a couple of years ago from one of their people, and they indicated that today this is very much an ensemble approach, where they combine multiple results together to do their recommendations, and of one of which is this kind of classic recommender engine. Other things include things like neural net, stuff that we'll talk about this afternoon, and clustering, and you combine them together and you get the best results, which is typical of a lot of approaches on this kind of stuff.